Yeah, so it's the day three. Now we're on to the third chapter of this Writing Innovation Rush by Philip. So let's go and let's get started. VGA text mode. The VGA text mode is a simple way to print text to the screen. In this post, we create an interface that makes it usage safe and simple by encapsulating all safety in separate modules. So we will just encapsulate all in safety in different modules or in separate modules other than the main RS, I guess. We will also implement support for Rust formatting macros. What's formatting macros? Let's take a peek at this and we'll just go back. These are the formatting macros from the form family. These are the currently implemented are these, reprint, printers. These are the formatting macros. Okay. So we'll support these as well. The blog is openly developed on GitHub. Yes, so you can see it. Complete source code. I just copied something because I'm very slow at writing stuff. To print a character to the screen in VG text mode, one has to write it to the text buffer of the VG hardware. So if you have to want to print something to the screen in the VG text mode, we have to write it to the text buffer of the VG hardware. So we need to give some of code like we did on the last time. To write something interesting. Yes, we know that. The VJ text buffer is two-dimensional array with a typical 25 rows and 80 columns. So VJ buffer is a 2D array to be easily. It is a 2D array definitely with 25 rows and 80 columns, which is directly under the screen. Let's explain it to you. Each array entry describes a single screen character through the following format. So now it is a 2D array with 25 rows and 80 columns. Where each array entry, like the zeroth row and zeroth column, is in the following format. So it has 0 to 15 bits. So it's 2 bytes, right? It's 2 bytes. So the first byte is 0 to 7 is an ASCII code point, and then it's divided into three parts. How can you divide eight into three parts? So it's 8 to 11 is the foreground color, 12 to 14 is the background color, and 15 is the blink. 15th, the last bit is the blink, and others for colors, and the first eight are for sky code points. Let's see what the blink is actually. These are very understandable. Let's start to make blink if they have any clarifications. The first byte represents the character that should be printed in the ASCII encoding. To be more specific, it isn't exactly ASCII, but a character set named code page 437. Huh. So it's not ASCII, it's another character set with some additional characters and slight modification. For simplicity, we will proceed to call it an ASCII character in this post. Also, I'll call it as I will not open this. Even though I do want to take a peek at this sky too. I can see the weird. Okay, it's not good. Why are you using it by the way? The second byte defines how the character is displayed. The first four bits define the foreground color, the next three bits the background color, and the last bit whether the character should blink. So I don't know why did they add this functionality that the character should blink. So it's cool. Uh, the following colors are available. So we have 0 is black, 1, 2, 3, 4. These are blue, green, cyan, red. Still all these colors. Now there is the bright bit. I guess the bright bit is connected to blink. I guess. So to 7 it's these, and to 8, 9 A, B, C, D, E, F. So it's like hexacoded, right? It's hexacoded. Dark gray, light blue, green, cyan, light red, pink, yellow, white. These are the normal colors, these are the bright colors. Like black is contradictory to dark gray, blue is contradictory to light blue. These are the darker colors for each one. The bit 4 is a bright bit, which turns, for example, blue into light blue. Yes, that's it. You just comprehended that. The VJ text buffer is accessible via the memory map dial to the address 0xb8000. This means that read and write to the address doesn't access the RAM, but directly access the text buffer on the VJ hardware. I have to read that twice to be honest. The VG text buffer is accessible via the memory map dial to the address. Yes, we have read this in the last chapter. This means where we manually encoded the value and print the hello world. Did you remember? This means that reads and write to that address doesn't access the RAM, but directly access the text buffer on the VG hardware. So it doesn't access the RAM, but yeah, I get it. Now I get it. So it doesn't access the RAM, it accesses the text buffer. Note that the memory mapped hardware might not support all RAM operations. For example, a device could only support byte-wise reads and return junk when a U64 is there. So we can only, this is an example, a system could only read byte-wise and might not work well for a U64. Fortunately, text buffer supports normal reads and writes, so we don't have to treat it in a special way. So we can use a U64 if they want to say that, I guess. We can play in the ground field like we can throw the ball anywhere in the ground. We would be safe. That's what tech prefer, I guess. A Rust module. Now that we know how the VJ buffer works, we can create a Rust module to handle printing. I have already did it. We've created the Rust module over here. Now, for the content of this module, we create a new src vj buffer.rs. I have also created that as well. Yeah, I created that. Manually coded it. So here is the first part. For the content of this module, we create this colors. First, we represent the different colors using an enum. Now it has allowed dead code, derive. I don't know what is this. Leave a clone, copy. We have all this. Yeah, we have all these, and we have REPR UX. Is it representation? Let's see. So here's an enum color with the hard coded values, white till the first last, and till this, uh, where we tell how much you were able to do the colors. Till 7 we were used to do colors. Till 0, yeah, counting from 0 to 7 we were used to do colors. Then these are the uh, bright colors. So yeah, you can. I got it too. What are these? We use a C like enum here to explicitly specify the number for each color because of the REPI U8 attribute. Each enum variant is stored as a U8. Actually, 4 bits would be sufficient, but Rust doesn't have a U4 type. So the REPR U8 attribute is a representation attribute, I guess. They haven't specified where to read more about it, but it is attribute which helps you to modify the enum variants into U8. They wanted to use U4, but Rust doesn't have U4, so they are not using the U4. Okay. Now, normally yeah, because it's 4 bits, right? Like look here, we can make sure we can do 2, so we can do 4, but Rust doesn't have 4. Get it? Where were we? Normally, the compiler would issue a warning for each unused variant. By using the allow dead code attribute, we disable these warnings for the color enum. So for color, if you just go for red and if we go for color like a bright bit, like it's a bright bit, so we go for red and we go for the red is pointed to +7, +7, it's 11. So no, I'm wrong. So it's +8. So light red. So we would use red and light red, but we won't use others. So we need something to uh, uh, dead these warnings, so we are using dead code. So this allows us to disable these color warnings. By deriving the copy, clone, debug, partial, and EQ traits, we enable copy semantics for the type and make it printable and comparable. What is this? We enable copy semantics for the type and make it printable and comparable. I have to understand this word. I may not remember this as well. Semantics. Copy semantics. Yeah, is it? So these are for the copying. Is an I-32, which means, yup, we did this, we did this. Now, if we had user types that do not implement the copy rate, we would have gotten a compiler because we tried to use a move value. There are some types which have copy rates. All primitive types implement the copy rate and the ownership is therefore not moved like one would assume. Following the ownership rule. To give an example, the following will only compile because the ICT rules have implemented the copy rate. So, copy trait is normally implemented in all the types we use, and thus we need to implement it over here as well to maintain the ownership factor. Else, if we throw error, I say get it in the type and make it integrable compatible. Yeah, this is very necessary. To represent a full color code that specifies foreground and background color, we create a new type on top of it. So, to represent the full color code, we need to create a new type on top of UH. So let's create this new type. Look who had done it. I have done it. So yeah, it also has these copy semantics for that, and it has representation transparent. I don't know what that is. So now we have a struct color code, and here we have implemented it. Here we have implemented it, and does it use a color? It uses our color for the foreground color and the background color, and it returns this color code, which is a struct of U8. And what it does, it compares the background as U8, and then if it's less than 4 or foreground as U8. I don't know what's this. Is this is this to convert something? I guess it is to convert to something uh, understandable mm, bit. The color code struct contains the full color byte containing foreground and background color. Like before, we drive the copy and debug traits for it to ensure that the color code has the exact same data layout as U8. We use the representation transparent attribute. So the color code should have exact same data layout as U8. We pass this representation transparent attribute. But it is U8, right? So what we pass in is this grid layout and use representation transparent. This is kind of shady practices we do here, right? Text buffer. Now we can add structures to represent the screen character and the text buffer. Let's add structure yeah, I get it. That's good. Who wrote this stuff? I- Why did I not write it over? It's cool. Now we have the derived. Yeah, we're doing this all the time. And what does representation seed now means? They're throwing so much representation stuff at this. Information attribute. This is like kind of I had to search it. Well, so let's read this because these is being used a lot and their explanation is quite short. So the representation, I was reading it right. I don't know. First and foremost, all types, how much longer it is to read. Just read this. Let's see how much. Yeah. So it's It's a small read. Let's read it. Sorry for the flashes, y'all. I'm just studying in a big room, so I'm all right. First and foremost, all types have a alignment specified in bytes. The alignment of a type specifies what addresses are valid to store the value at. A value with alignment n must only be stored at an address that is multiple of n. So, alignment 2 means you must be stored at an event at even address, and 1 means that you can be stored anywhere. Alignment is at least 1 and always a power of 2. So 2 to the power 0 is 1. I'm a genius. Primitives are usually aligned to their size, although this is a platform-specific behavior. For example, on x86, U64 and F64 are often aligned to 4 bytes, 32 bits. Uh, type size must always be multiple of its alignments, 0 being a valid size for any alignment. This ensures that any array of that type may always be indexed by offsetting a multiple of its size. Note that the size and alignment of a type may not be known statically in the case of dynamically sized types. Yup, if it's dynamically sized, how could we know its alignment? Rust gives you the following ways to lay out composite data. So, to find alignments, now we can uh, do it in the dynamic size types as well. We do it in tuples, arrays, structs, enums, unions, untagged unions, not all of the unions. Uh, an enum is said to be fieldless if none of its variants are associated data. Ours is fieldless as well. By default, composite structures have an alignment equal to the maximum of their fields alignments. So if it's U32, so the U32 should be yeah, it looks like that. Rust will consequently insert padding where necessary to ensure all fields are properly aligned, that the overall type size is the multiple of its alignment. For instance, this is the one and will be 32-bit aligned on a target that aligns these primitives to their respective sizes. The whole struct will therefore have a size that is multiple of 32 bits. Yeah, it has a padding of 3, so 8 times 3 is what? Uh, I don't know, 8 times 3 is 24. 24 plus 8 is 32. So yeah, it's padded 32. It's 32, and you do the twice of it, so 8 times 2 is 16, and now you have 16, so you have 16 bits now. Or maybe struct A, B would be 32, then you 16, then 8. So you could store it this way, but this should be 32, then the another space should be after 32. I mean, don't print it. I don't get it this one. There's no indirection for these types. All data is stored within this block, as you would expect in C. However, with the exception of arrays, which are densely packed and in order, yeah, you can jumble like a struct, right? You can jumble uh, the types, but you can do you don't jumble the types. You just jumble the B, C, and A. The layout of data is not specified by default, given the two following struct definitions. So you can't jumble like these in arrays, but the layout of data is not specified by default, given the following two struct definitions. So A is isolated, B is U64, and the struct B is isolated. These are literally identical. Rust does not guarantee that two instances of A have their data laid out in exactly the same way. However, Rust does not correctly guarantee that an instance of A has the same field ordering or padding as an instance of B. Rust doesn't guarantee that. So what does it guarantee? With A and B as written, this point would seem to be pedantic, but several other features of Rust make it desirable for the language to play with data layout in complex ways. I don't get it. This point would seem to be pedantic. Yeah, it seems weird. So I don't know what pedantic means. Should I Google it as well? You can Google it. DuckDuckGo. Pedantic is a characterized a narrow something like that, like a pendant. I had to study. But several features of Rust makes it desirable for the language to play with data layout in complex ways. Yeah, complex is better. For instance, consider this stuff. We have uh, identifiers, count as U16, then data is T. There's these types stated here. Now consider the monomorphizations of foo, and so you have swapped the types. If Rust lays out the fields in the order specified, we expect it to pad the values in the stuff to satisfy their requirements. So if Rust doesn't reorder fields, we would expect it to produce the following. Uh, Nice. These are the basic padding here. But they haven't taught us the reproduced rate. Nice. I like it. We are so deep inside. We don't know what's represent transparent and represent C and represent mu. But I get it. It fixes all of this. Enums make this consideration even more complicated. Naively, an enum such as this might be read out as this AC U64 and where is zero is A is C. Many times I am more of book. I'm now more confused. Sorry for this murmuring voice. I'm confused than ever. Since the field lord, let's read more function blog. Hmm. Since the field ordering in default struct is undefined in Rust, we need the represent C attribute. Guarantees the struct fields are laid out exactly in C struct. But that is what Rust does, right? And thus guarantees the correct field ordering. Oh, I get it. What we learned, right? Rust doesn't give padding because it jumbles up. But C doesn't jumble up. So we use the representation C to make it not jumble up. This was all the stuff we need to read. We need to read the block first, right? Just basic like 10 minutes over there. For the buffer struct, we use represent transparent again to ensure that it has the same memory layout as its single field. For really weird buffer. We didn't use I didn't wrote it over here. So try that. So for the buffer, it's buffer height, right? What is this lethargic looking code? Screen cadet. I guess I have used from the repo. I guess that's why the code was changed a bit. Scope it. Just scope it. So it's a screen character buffer width, and you have the buffer height. So these are characters, and then there is the buffer height, the screen. Now what does it hold? Does it hold the U size? Yep, it does. Since the field, yep, we got it. To actually write to screen, we now need to create a writer type. So let's create a writer type. It will be a structure where the column position will be U size and the color code will be color code that we did up. And so it's a U8. It's a U8. You already use the representation create over attribute over there as well. Buffer. So buffer is mutable. What it does? Static mutable buffer. Buffer is why are they passing this to buffer? The writer will always write to the last line and shift lines up. And so writer will always write to the last line and shift lines up when a line is full or on the backlash and the the column position field keeps track of the current position in the last row. The current foreground and background colors are specified by color code, and a reference to the VJ buffer is stored in the buffer. Note that we need an explicit lifetime here to tell the compiler how long the reference is valid. So we use a lifetime static over here, and it specifies that the reference is valid for the whole program runtime, which is true for the VJ text buffer. So we have introduced the lifetime, and this is valid till it's valid till the whole program runtime, which is true for the VB technique. So we will use this writer and we run this function for during the runtime. So this will be valid throughout the runtime. So we won't lost it after this is run because now we pass it explicitly with the lifetime, and the lifetime expires after the program completes during the runtime. Now for the printing, this is where we introduce the writer type. Let's come to the God works where we just print something to the screen. Now we can use the writer type to modify the buffer's characters. First, we create a method to write a single ASCII byte. Now we can which is right. Oh my God, this is a very bad code. I have to use this. Let's just copy paste this. I'm using my laptop, so sorry for that. Not in the correct position as well right now. So let's implement this writer. And now for the pub function write byte, mute shelf, and byte is mute as well. So we have a match in US, which is it is quite famous. So it matches byte, and if it's true, it did some kind of backlash and a confirmation, and it switches to the new line. Self is a pointer, it's passed over here, which is going to be the last line to be explicit as this had. Then it goes to byte, and if the self dot column position is less than the buffer's width. So we have stuff to write, right? So it's greater than, sorry, it's greater than. So we don't have stuff to write, so we just shift to the next line, even though we don't have a backlash n. Now let row is the buffer height minus. As we have shifted to somewhere, right? We obviously did something now in the next line, so we should decrease the buffer height. So now it should, yeah, should decrease. Let column is equals to self dot column position. So it's, I guess it's the first position of the column. It should be right there. Now, no, we did just shift it to the row. If you shift the row from the last position, I guess this should shift to the column position in the first, which you stated. This is like clean code. Let color code is equals to self dot color code. Yeah, this is definitely now the self dot buffer dot cars, which is the buffer. Yeah, like you remember, the VJ buffer is a 2D array of 25 or 80, I guess 20, yeah, before 25 80. And now we have used the screen character uh, type above the struct. Now we just pass the ASCII characters, which was the byte, and now we don't need to write color code like that. We just pass the color code here directly. So this handles all of our printing on the screen. And so it also it's a write byte function. It writes single byte. So yeah, it does it. Now the self dot column position increases. Yep, it's very easy code to write. And here we can need to implement the new line. If it stays right, we can do this, right? This is very easy. This one was very easy. If the byte is the new line byte, that is backlash n, the writer does not print anything. Instead, it calls a new line method, which we'll implement later. Other bytes get printed to the screen in the second match list. Let's see how much time has passed. Where do you see the time passed? Here. We have just, oh, we have 30 minutes of time. We are so late. Let's just go through fast. Uh, it's late in the night as well. It's 12:52. So where were we? When printing a byte, the writer checks if the current line is full. In that case, a new line call is used to wrap the line. Then it writes a new screen character to the buffer at the current position. What does that mean? Finally, the current column position is advanced. Yeah, I read it. So I know it. Probably I know it. The print whole strings, you can convert them to bytes and print them one by one. So it will be an easier function for us. Let's implement this. The copy one, two. No, let's copy this whole. Now we use the write string function, which takes helps of the write byte to write single bytes. What is this printable sky byte or new line? The VGA text buffer only supports ASCII and additional bytes of code base 437. So VGA text buffer supports them. Okay. The rush strings are UTF-8 by default. UTF-8. I read it somewhere, now I don't recall it much. So UTF-8 is the yeah. UTF-8 is the standard one. These are the UTF-8, first byte, second byte, third byte. Here we can calculate the number of free bits. It's 16-bit unit code and UAT sequences like this. So it's 1, it's stored 1, 7F, it's stored 7F, FFF, it's stored EF, PF. So this is a way of storing. So here, I guess they have did this the same. So they might contain bytes that are not supported by the VJ text buffer. So UDF is vast, and you just saw they have US and OF, EF, BF, PF, which VJ might not understand. So for that, we use a match to differentiate printable SKY bytes, a new line, for anything in between a space character and what do you call it? I call it kiddy character and unprintable bytes. So whatever is unprintable and whatever is new line, we just don't write it, or we do what? I don't get it. For unprintable bytes, we print box character which has the box code 0xFE on the VG hardware, and so also for whatever we can support, so for this sky bytes we print it, and if it's /n we pass it as well, because we have handled the case for backlash n in our write byte function. So this is what we print. So anything there else other than this is printed as in form of this square character, which is 0xFE on the VG hardware. It is 16 bit, I guess. 16 byte bits. Try it out. To write some characters to the screen, you can create temporary function. So let's create a temporary function in the VG buffer as well. Only let's do this. Mm. Now we have the print something function. Let's read what it does. It first creates a new writer that points to the VG buffer at 0xP8 to 1000. Where does it point to? Doesn't it does it does over here. The syntax for this might seem a bit strange. Now we can see the whole code. It's, keyboard's a bit sensitive. Bro, it's too sensitive. Ah, what's up this? Oh my God, this is now fine, I guess. Yeah, we this yeah. The syntax for this might seem a bit strange. First, we cast in integer 0xp8000 as a mutable raw pointer. Yep. Then we converted a mutable reference by dereferencing it and immediately borrowing it again with a mutable. Yeah, this was yeah. If why didn't you do it the first time? Because it was a pointer and then you converted it to a mutable reference. So we have to dereference the pointer, then convert it to a mutable reference. I get it. This conversion requires an unsafe block, so it's unsafe, Rust. It's unsafe. You don't do this practice often. Yeah. Then it writes the byte h to it. So we have the buffer, we have the place where we were able to write the text buffer, and here we pass the byte bh to it, and the b prefix creates a byte literal, which represents an ASCII character. What's a byte literal? A byte literal is a single ASCII character in U plus 00 to U plus 007F range, or a single escape preceded by the characters U plus 0062B and followed by the characters 0027. If the character is this, the present within the literal, it must be escaped by a preceding U. I don't know what's this. I guess something's a lot meant to be understand. Uh, I just change it. The blog might explain it. Blog explains it. Uh, a B prefix creates a byte literal, which represents an ASCII character. So byte literal B is an ASCII character. By writing the strings B, H, L, LO, and word, we test our write strings method. So why didn't we write hello at the sequence? Why did we use the B? B is a byte literal. And what's byte literal? We don't know what's a byte literal. Byte literal, uh, easy explanation. You don't need those buzzwords. Rust. We did open this, we didn't understand it. GFG would be able to explain this to us. It is a Reddit post about it. Someone else explained it. Any string prefixed by a B tells the compiler that the string should be treated as a byte sequence. This is called a byte string literal. You can read more about this. In a short setting, a string is a Rust in a valid sequence of Unicode characters. So, string is a sequence of Unicode characters, and hence it can be represented as uh, mutable aid, nuid, a slice. It's the slice containing unsigned 8-bit integers. A byte is also a 8-bit integer, so it is considered as a sequence of Unicode. So now it creates this sequence, which is 4 and 4. So it's for creating a so like the hash dot right function takes a unsigned aid actually, and it is a sequence of bytes as a parameter. In order to convert your string to bytes, you prefix it with a B. So yeah, we need to print the string, right? And to print the string, we need to first convert it into the byte to create the sequence. To create the sequence that it is a sequence, it's a Unicode sequence. So we use the B literal. For example, they have all these steps. I get it. Yeah. So we test our right string method as well because it prints the bytes byte by byte, which is simple string. And the handling of the unprintable characters. To see the output, we need to call the print something function from our start function. So let's just copy this. Let's go to the main RS and change the so it's the same. Let's go. Should we delete this because we're not using this one? So it should uh, do it. Create another fresh terminal for us. Just go cargo build. To fail with some user that I will tell. In which this remove it. You don't need it. Remove this as well. This is that code. We don't need that code. What? Why is not found in DJ buffer? We did have this, bro. What the fuck? We did add it, and then why it is not there? It is there. It is there. Are you dumb? Bro, what the fuck is this? Let me fix this up. I'll just pause the stream again. Yeah, so we fixed it. It was just not well written. I just passed the print something inside of the implementation. I just passed outside of it. Now let's just cargo run. It should open up something like this. Um, in place of O, there is two boxes. Here's our screen. Something is loading. Something is loading up. Let's wait. Why don't you watch something like this on 2x? It would be very favorable if you want to watch till the end. It's not opening, guys. It's not opening. It's not opening. Is it our screen? It's not. Why you haven't? Let's wait till it opens. So I did a lot of debugging, but I wasn't able to fix the issue. Probably it's something with the code or the versions. I guess we'll when I just follow this. So let's do it this much for today, and let's go for the next day and complete the volatile. I guess this should work. This had worked for me like all this time. This much of code shouldn't break stuff because we didn't actually do anything. We just use these attributes, which were uh, in Rust, right? When import something, you use a dependency. So yeah, so we'll come tomorrow with volatile and probably try to fix this. It's late now, so I won't be able to fix it now. Yeah. So let's move to the day four and GG's. Let's see where we go ahead and complete this blog. Bye. Don't be crazy if I say bye. It stops recording. But it not. It doesn't. It doesn't. I should do anything upload.